going to talk about why charge does not transfer immediately, why it takes some time for charge to transfer through a wire, why batteries don't immediately exert all of their potential difference. And the reason is something called electrical resistance. We're going to set up a relationship between electrical resistance, voltage, and current, something called Ohm's law. The first thing I want to take a look at here is, let's say we have our circuit here. We have a circuit, a simple circuit. The circuit has a closed pathway to travel. We see a closed pathway to travel around a battery. I also want to start getting us familiar with some of these symbols. These symbols are on page 4 of our reference table. They're on page 4 of the reference table in the bottom left corner. And I'm using a couple of them now. I'm using, for example, this line to show a wire. And I'm using these series of small lines and big lines to show a battery. And we want to remember a battery is also a potential difference source. The battery has a certain voltage. It has a potential difference. Those symbols we want to get familiar with on the bottom left corner of page 4 of the reference table. Take a look at page 4 of your reference table right now. We take a look at this and we might say to ourselves, okay, I know we have a negative charge and a positive charge, and I know it wants to transfer, it wants to balance out. Well, what's stopping this from just all balancing out immediately? Why is current a rate? Why does it take time for that charge to transfer? And the answer is that each electron in sequence is bumping the electron in front of it, and bumping the electron in front of it, bumping the electron in front of it, bumping the electron in front of it. The original electrons from this charge are not the first ones that get to the other side. It's kind of like if you went online at a theme park. Yeah, you're the last in line. The people in front of you go, you move into their spot. The people in front of you go, you move into their spot. The speed at which that line moves is the current. The thing that is restricting that speed of that line is something we call resistance. And because normally charge would just transfer immediately from a potential difference source to equilibrium, but it doesn't do it immediately, we know that there's an electrical resistance. Let's talk a little bit about this electrical resistance. Very simply, this electrical resistance is the ratio of the potential difference over the current. It's the potential difference over the current. And this relationship, R equals V over I, is something called Ohm's law. It connects 3 very important values: resistance, voltage, and current. If, for example, I said a current of 3 amps is produced by a 9-volt source. Well, you might say to yourself, well, what is the resistance? What is the resistance in this circuit? What is the resistance in this circuit? And I would say very simply, well, what is our resistance? We'd say our resistance is the voltage divided by the current. So the resistance here would be 9 volts divided by 3 amps. And you'd get a resistance of 3. Our question is, well, what is 3? It's voltage over amps. It would be 3. We have a unit for ohms. We have a unit for resistance, and that unit is the ohm. And it's going to have that little horseshoe symbol there. We'd have 3 horseshoes, 3 ohms of resistance. So you can say to yourself, resistance is slowing the current down. Resistance is slowing the current down. It stops the progress of that current. The current wants to flow freely, very rapidly, but resistance is going to slow it down. And we have a little chart here that shows the values we've talked about so far. We've talked about charge, or Q. It's measured in coulombs, and usually a coulomb is 1.6 times 10 to the negative 19th times the elementary charges. Voltage, V in volts, also called potential difference. This is also called potential difference. And that's going to be measured in volts, and that's work divided by charge. We have current measured in amps, that's at I, and it's charge divided by time. Remember, that's charge in coulombs divided by time. And finally, we have resistance. This is our newest one. We're going to use R for this in our symbols. It's measured in ohms, and we have an equation we haven't talked about yet to calculate resistance independently. But essentially resistance, measured in ohms, is the ratio of voltage to current. This equation, Ohm's law, extremely important equation. Extremely important equation. So I want to say, well, what is resistance? Resistance is the tendency of the materials to resist the flow of current. It's what slows down the flow of current. And a resistor in our diagrams is often going to look like this. And once again, you can find this on page 4 of your reference table. You can find those jiggly lines on page 4 of the reference table. A lamp has electrical resistance. Anything that's like conducting current essentially has some electrical resistance, including wires themselves. The wires themselves also affect your electrical resistance. And that brings us to this equation. We could say, okay, well, I calculated voltage independently, work over charge. I calculated current independently, charge over time. What about resistance? Well, I know it's voltage over current, but I can also calculate it independently. You can calculate resistance independently using this equation. Resistance is equal to rho times length divided by area. And this is the resistance in a wire equation. If I want to find the resistance in a wire, there are 3 things that affect it. The first one is the length of the wire, and that's going to be measured in meters. The length of the wire in meters affects your resistance. The longer the wire, the harder it is to get to the end of it. So higher length, higher resistance. This symbol right here means resistivity. It has to do with the material of the wire. It has to do with the material of the wire. So we have the resistivity of the material. You might be saying, well, wait a second. I've dealt with things in physics where I had different materials. I dealt with things in physics where I had different materials. What do I have to do with different materials? You go to your reference table, you find that material. Here, resistivity, page 4, bottom right corner. So we see our bottom right corner here has different materials. Silver, for example, has an extremely low resistivity, meaning it's a very good conductor. That's a very important point. Good conductors have low resistivity and therefore have low resistance. They transfer a lot of current. So good conductors have very low resistance, very low resistivity. So resistivity, that's the material. You're going to find that on page 4 of your reference table if they ever say a material to you. And our last thing here, cross-sectional area. Imagine we have our wire, and imagine I cut the wire, and we notice, oh, it's kind of a circular thing here for the wire. I cut this wire in half, and we see there's this circle here. The area of that circle, that's A. That's your cross-sectional area. Your cross-sectional area basically means if I cut the wire in half, how wide is the wire? You could think of this kind of as the width of the wire. And you might notice as the wire gets wider, it has an inverse relationship with resistance. So a wider wire means lower resistance. So let's look at some relationships here. A long wire means high resistance. A conducting wire, a good conducting wire, meaning a low resistivity, means low resistance, meaning it has low resistivity, so it conducts very easily. And a fat wire, meaning the cross-sectional area is very high, is again low resistance. That the width of the wire itself is going to affect this. Another analogy I like to use is that of a river. Imagine the current as water flowing down the river. Right? Current is the water flowing down the river. The voltage is the water source. Bigger voltage, bigger current. You have a bigger water source, you're going to get more water down the river. Like if it rains like crazy, you're getting a very fast current down that river. The resistors are kind of like logs and stones and things that block the flow of current. They block the flow of current. Now if you want to say to yourself, well, what's going to happen here for this resistance to be very high in the river? If it's a very long river, it takes a long time to get to the end of it. If it's a very wide river, it's very easy to get to the end of it, whereas if it's very narrow, it takes a long time to get to the end of it. And if the material itself matters, if I filled the river with molasses, it's going to take a much longer time to get to the end than if I filled it with water. So the resistivity of the material affects it, the length, and the cross-sectional area. Sometimes you will have to calculate the cross-sectional area, because it is a circle. How do we calculate the area of a circle? Well, you have your radius, it's pi r squared. So A can sometimes equal pi r squared, the equation of a circle. One last thing that affects resistance and that we might not expect. A higher heat. If it's hot, if the wire is hot, if it gets warmer, we have a high resistance. And you want to remember, high resistance means low current. So if it's hotter, we have a lower current. Always remember this. High resistance equals lower current, assuming voltage is the same. There's a lot of ideas to unpack here. We're going to spend several days on this, but that's Ohm's law and electrical resistance. We now have a relationship between voltage and current. It is electrical resistance that is slowing it down. We have some new symbols on page 4 of our reference table. This equation is also on page 4 of your reference table. We have this very convenient symbol chart, certainly worth writing down if you have not done so already, and I will also post something like this on the Harvard, so you have access to it. And we also have an independent equation for resistance, and we see that the material, the length, and the cross-sectional area, as well as the heat, all affect how likely a current is to travel, how good of a conductor you're dealing with.